the laws that govern motion, drawn together by one man, Isaac Newton. Newton's laws may read a bit like a legal document, but in mathematical form they are simplicity itself, and in that simplicity lies their strength. The search for an adequate model for motion stretches back as far as civilization itself. At first, progress was slow. In the 5th century BC, Parmenides argued that all motion was impossible, that our impressions of movement are mere illusions. Fortunately, this extreme view didn't last for long. It was Aristotle who eventually formed a common sense model of motion, which was accepted by his contemporaries and then for a further 2,000 years. In medieval Europe, scholars were still locked into this classical frame of mind, and Aristotle's model went virtually unquestioned. But the Renaissance brought a wind of change, in science as in everything else. Copernicus, Kepler, Galileo, and others. They all started to question Aristotle's teaching. And what's more, they could back up their doubts with experiments and observations. Even the authority of the church couldn't conceal the cracks that had developed in Aristotle's model. A new theory was needed. The new age of mechanics dawned in the 17th century when Isaac Newton proposed his laws of motion. His influence on contemporary thinking was remarkable. Not only did Newton come forward with the laws of motion, but he also provided the mathematical tools to apply them. The method of fluxions, or calculus as we know it today. Future mathematicians and scientists were able to apply Newton's laws to a vast range of problems, but all of them building on the insight of Newton. Newton's laws were the watershed of scientific thought, and they are no less important today than they were 200 years ago. From the design of sewing machines to the launching of space probes to Jupiter and beyond, it's Newton's laws that form the basis of the model. They allow us to predict and to plan complicated motions. So powerful are Newton's laws that it's hard now to imagine a world without them. So what was life like before Newton?
Well, what was life like before Newton? How did people explain motion? For example, the motion of this card. Well, at first sight, you might say, the natural state of motion of the cart is to be at rest. Whoa! Well, if I wanted the cart to keep moving, then this horse would have to keep pulling. In fact, it would have to exert a force. Well, in fact, the horse would have to exert quite a large force indeed. So, you might actually believe that the natural state of motion of the cart is at rest. Consequently, whenever you see something moving, you might believe that there has to be a force acting on it to keep it going. Well, that sort of makes sense, doesn't it? Well, it made sense to people for about 2,000 years, from the time of Aristotle to the 17th century. It took the genius of Newton to realize that these common sense ideas are not the best way to model motion. The clue to understanding motion comes from considering much simpler things. You see, the cart is complicated. There are all sorts of hidden influences acting on it. One of these, for example, is the friction due to the roughness of the road and the roughness of the bearings. Now, what would happen if we try to cut down on that friction? Well, a smooth ice rink gets rid of a lot of the friction. and it's level, so there's no effect of gravity either. Well, what's going to happen to motion under these conditions? For example, to the motion of an ice puck. Well, once started, an ice puck will move across the ice with almost constant velocity in a straight line. Well, even an ice puck will slow down and come to a halt. You'd think that for any particle, you'd need to keep applying a force in order to keep it moving. Well, that's what people thought before Newton. They thought, where there's motion, there must be a force. But Newton said, no, that's not the case. A free particle, that is, a particle without any forces acting on it, must either remain at rest or move with constant velocity in a straight line. And that's just a statement of Newton's first law. It means that you don't need any special explanation to explain uniform motion. That's what happens in the absence of external forces. But what about this sort of motion? Each time it's struck, the puck's motion changes, and Newton would say that indicates that a force has been applied. In between hits, the puck is behaving almost like a free particle.
So, there's a connection between the force and the deviation from uniform motion. That's Newton's second law. Newton's laws have wide applications, and it's studying those laws and their applications that we call applied mathematics. Now we look at the question, what relates force to deviation from uniform motion?
Newton gave a very definite answer to that question. The form is F equals ma. Force is equal to m times acceleration. Now, m is a constant, which we'll have a lot to say about later on in the program. But for the moment, the important thing for us to notice is that force is proportional to acceleration. Acceleration, the deviation from uniform motion. Well, what does that mean experimentally?
To have a closer look at Newton's laws, we've set up this piece of apparatus, which does the same sort of job as the ice rink, but even better. To cut down friction, this glider rests on a cushion of air. The air coming through tiny holes along the track. Just like in the ice rink, this is level, so gravity is not going to affect the motion. And of course, by using a track, we can find ourselves to one dimension. That's what we're doing throughout the unit. Later in the course, you'll see how to extend the ideas we develop here to 2 and 3 dimensions. But for the moment, let's just look at the simplest possible case, a free particle in 1 dimension. These after images are left on your screen by a piece of electronic processing. What we've really done is to freeze the position of the pointer on the glider every 3/4 of a second. So you see where the pointer was at 3/4 of a second, 1.5 seconds, and so on. Now, the equal spacing of the images means a constant velocity, or 0 acceleration. And that's just Newton's first law. With no force, the glider was just a free particle. But Newton tells us much more than that. Newton tells us what happens when we do apply a force. F equals ma. Force is proportional to acceleration. So, if I apply a force, by attaching this string to this glider, we should see an acceleration. Well, now the after images are getting further apart where the glider's speeding up. And from those after images, we can find out something about the acceleration. We start by looking at the graph of distance against time. The timing started when the motion started. After the first time interval of 3/4 of a second, the glider had travelled 0.05 meters. After the second interval, 0.22 meters. And so on. So over the whole period, the distance time plot looks like this. We can get a velocity time plot from this. To get the velocity at any instant, we need to differentiate. We can do this by drawing tangents. At the start of the motion, the tangent has 0 slope, 0 velocity. The glider started from rest. After the first time interval, the tangent to the graph has slope 0.15 meters per second. After the second time interval, the slope is 0.3 meters per second. And so on. The velocity time graph that we get from that is a straight line graph. The velocity changes at a steady rate of 0.2 meters per second, a constant acceleration. What would Newton have made of that? Well, Newton would have said straight away that the constant acceleration must have been produced by a constant force. You see, F equals ma, so if A is constant, then F has to be constant as well. And that's something we can check directly, because the more force I apply to this spring, the more it stretches. So if a constant force is really being applied, the string should have a fixed extension. There it is, a constant extension, a constant force. Just what Newton would expect. Now let's try a different force on an identical glider. We'll adjust things at this end so that the force is twice as large as it was before. And to check that it really is twice as large, I've got 2 springs here, 2 springs just as I had before, side by side, and they've got the same extension as they had before. So the 2 springs indicate double the force. Well, obviously the glider accelerates more rapidly under these conditions. I don't want to go through the acceleration analysis here, so I've left it as a problem for you to do after the program. But you should find an acceleration of 0.4 meters per second. That's twice the acceleration we had before. So with double the force, we have double the acceleration.
And with 3 forces, we get 3 times the acceleration, and with 4 forces, 4 times, and so on. And that's what F equals ma means, that the force is proportional to the acceleration. Well, I promised that we'd say a little bit more about this constant m. Suppose I were to do John's experiment with 2 identical gliders stuck together instead of this single glider. Well, I don't think it needs much imagination to realize that it's going to be harder to accelerate this one. For the same force, this one is going to go to a smaller acceleration. So in this equation, that means for the same force, as this acceleration is going to be less, then this value of m has got to be greater for the bigger glider.
an acceleration of 0.1 meters per second per second. That's just half the acceleration we had with a single glider pulled by the same force.
Again, we can see what that means in terms of this equation. For a single glider, the acceleration was twice as much for the same force as it was for the double glider. That means that the double glider, this m, was twice as big as it was for single glider. And for 3 gliders, it's 3 times as much. For 4 gliders, it's 4 times as much, and so on. So you see that this number m, which depends on the object, tells us 2 things. First of all, it measures the reluctance of the object to be accelerated. And secondly, it measures for us the number of gliders. And really, that explains the name that we give to this number. It's called inertial mass, or sometimes mass for short. Inertial because it tells us how we measure it. It measures its inertia to being accelerated. And mass, well, it really measures the amount of matter in the object. So that explains Newton's second law, F equals ma, force equals mass times acceleration. Well, now we have this equation, let's see what we can actually do with it. Well, so far all we can do really is measure acceleration. Now, if I'm going to quantify forces and masses, I really ought to adopt some conventions. For example, the convention for the mass unit is arbitrary. I could choose the International Standard Kilogram, but as you can see from this picture, I'm not going to be able to get my hands on that very easily. So I think it's far better from our point of view to pick as one glider, one standard glider, as our mass unit. Then I can measure force in terms of that. For example, remember in John's experiment, he found that when he had one glider, so that's one mass unit, he got an acceleration with the force he applied of 0.2 meters per second per second. And that means that when I multiply these two together, it's a very easy calculation, the force turns out to be 0.2 force units. So in fact, one force unit would be really about 5 times the sort of force that was applied in that experiment. Well, we can measure forces that way, but can we use it to measure masses? For example, what about this mystery mass?
We can find the unknown mass by an acceleration experiment. As usual, we'll use a force of 0.2 force units.
So, let me use our fundamental Newton's equation, F equals ma, to determine this mystery mass x. Well, what was that acceleration that John measured? It was 0.13 meters per second, and the mass, well, that's what we're trying to find out. I'll call it x. And the force he used was just the old force that he's been using all the time, which is 0.2 force units. Now, when I solve that equation, I get x is equal to 0.2 divided by 0.13, which, well, it turns out to be a little over 1.5 mass units. It's just about 1.5 times our standard glider. Well, in principle, we can use this to measure any mass. It may not be the way that you think that mass is measured, but this is really the fundamental way of measuring mass, as a measure of inertia.
So far, all the forces we've used have been applied to the gliders through springs. But Newtonian mechanics is about far more than springs. Look at this. I'll put a wedge under the air track so that it's tilted. Now, there's certainly an acceleration here. Where there's an acceleration, there must be a force.
Well, of course there's a force down the inclined air track. That comes about as an effect of gravity. But what's more interesting is that we can actually calculate the magnitude of that force. And we can do it on the basis of Newton's second law. F equals ma. Well, a, the acceleration, John's experiment has actually found that, and he got that to be 0.06 meters per second. And the mass, well, we've actually found that too. That mass is 1.54 mass units. So Newton's law tells me that if I multiply these together, I'll get the force in our force units, and that turns out to be 0.09. Well, okay, I suppose that's fairly satisfactory. But a theory is only exciting if you can make predictions. And, in fact, we can make predictions on the basis of this second law. But that will involve John doing a new experiment. And this is the experiment I'd like him to do. Let's consider that inclined air track, and suppose we have our glider on it, and he applies one of his standard forces upwards, and I know that we have this force that we've just calculated downwards. Well, what's going to happen? Well, intuitively, think of it like this. If you have two tug-of-war teams who are pulling in opposite directions, and they pull with equal forces, what's going to happen? Well, nothing. The forces will just cancel out. But that's not quite the situation here. Here I have a standard force upwards, which is 0.2 force units, and the force downwards, I've just got that to be 0.09 force units. So there's a residual force upwards because, well, 0.09's worth of this will just cancel from the 0.2 upwards, and what will be left will be 0.2 minus 0.09, which is just 0.11 force units upwards. So what do I predict? I predict that the mass will accelerate upwards with an acceleration corresponding to a force upwards of 0.11 force units. Well, let's see John do that experiment. .07 meters per second, this time up the track. Well, that acceleration is consistent with my prediction, as you can easily check after the program. Well, this might seem like a very trivial problem to you, but Aristotle couldn't have solved it. Only the insight of Newton in associating the acceleration with the applied force allows us to solve problems such as those. And Newton's laws just don't apply to problems such as gliders on air tracks. Well, we came here in the first place in search of a free particle, and we found that a nice puck was a fairly good approximation. But Newton's laws just don't apply to free particles. Even when there's friction, such as with the horse and cart, then Newton's laws still apply, providing we include all the forces. The law F equals ma looks very simple, but it's got very far-reaching consequences. In fact, Newton's theory has proved to be one of the most successful scientific theories of all time.
As part of the pre-module work, you've seen that displacements add using the vector addition rule. Now let's look at this system of weights and strings.
And now, what about forces? Forces have magnitude and direction. How do forces add? Well, take a look at this setup here. You can see two forces acting on the ring here. One force along this string direction,
the other force along that string direction. The force magnitudes are given by the weights here that hang on the other ends of the pulley. Now, there's also a third force acting on that ring. It's the force provided by the peg here that holds it steady. Could you determine what the force of the peg is? What's its magnitude and direction? Well, let's have a look. Let's assume that the two forces in the strings here can be added by the triangle rule. Well, we know their directions and we know their magnitudes. That means that we could draw geometric vectors, do a triangle addition, and find their resultant. But how would that help us? Well, it helps us because the peg is providing a balancing force. A balancing force equal in magnitude to that of the resultant of these two, but opposite in direction. So let's do that. Let's find that resultant. Well, I'm going to have some geometric vectors here, and perhaps, Anne, if you'll help me with some television magic. We need a geometric vector 8 units long to represent the longer of the two forces, and I see it's there already. And the other one has to be 6 units long. That's it, in the direction of the string. And now to add them by triangle addition, we have to move the longer until its tail is sitting on the head of the shorter of the two. And if you could now put the resultant in from the tail of the first to the head of the second. There's the resultant. Now, that resultant is 9 units long. I know that because I measured it before the program. I know from that the magnitude and direction of the resultant. Here's a force of 9 units provided by these weights here. And what I'm going to do is I'm going to apply this force to the ring. And I'm going to align its direction so that this force is opposite in direction to the resultant that we had on there. It's a matter of aligning the string direction. There it is, equal in magnitude and opposite in direction. Now, if we're right about this, then this third force is doing the job that the peg was doing, balancing the resultant. So if I take the peg out, the ring should remain held steady. So there we are, we don't need the peg anymore. So we started off by assuming that these two forces add by triangle addition, and things worked out. So I think that's pretty good evidence that forces do add by the triangle addition law. So now, let's have a look at another situation where vectors are adding.
There's another important area where geometric vectors turn out to be important, and it's really quite surprising. It's this situation. When something's spinning, how would you model that spin by a geometric vector? Well, let's look at it in more detail. Here's a disk that's spinning, and it's this spin that we want to model with a geometric vector. We need a length or a magnitude. That's not too bad, that's the angular speed. But what about a direction? Well, using the clock rule, this is spinning in a clockwise direction from where I'm looking at it, so it'll be a vector in that direction, like this. Now here it is again. A spin like that. Clockwise from where I'm looking at it, so it's a vector pointing away from me. Now I can arrange for this ball to spin in several different ways. Another way is like this. And that spin is a vector in this direction. What will happen if I turn on both motors at once, combining the two spins? Now that spin is clockwise from below, so it's a vector pointing upwards. Now let's see if the triangle addition rule will give us that kind of result. First thing to do is to move this vector so that it's adding onto the end of this one, like that. And the result then of this vector and that one is here. Indeed, a vector pointing upwards. Well, let's put that away just now and try a slightly different situation. I can switch this switch so that it rotates the ball like this. And that's a spin represented by this vector. Now again, if I switch this one like this, that's that vector. Now I want to see if I can use the triangle addition rule to predict what happens when I have both of these two together. Well, the first step is to move this arrow down here like that, and then the result is this vector going from here to here. That is a spin like this.
So, spin can be modelled by vectors, and those vectors obey the addition rule. You know that vectors have a direction, the line along which they act, a magnitude, the size, the amount of the vector, and you know that they add using the triangle rule.
But at this stage, we really ought to develop our model, because so far we've added our vectors using geometric vectors drawn on a page. And it's not always convenient to draw geometric vectors. Have a look at this practical problem here. What I've got here is a mock-up of a sailing dinghy. The mast here is being held in a vertical position by the 3 stays here. The forces in the stays are parallel to the length of the stays, and their magnitudes can be read off on the spring balance down here. So the situation we have is that there are 3 forces here acting on the mast. And it's important from the design point of view to know what the resultant force on the mast is, because it's acting in a downwards direction on the hull. And the hull has to be designed strong enough to support that force. So how could we predict the resultant of these 3 forces acting on the mast? Well, I don't think we could draw geometric vectors here because the 3 forces are acting in 3 dimensions. It's not convenient to draw. So what we need is a new model of vectors. We need a numerical model.
What we need to be able to handle 3-dimensional vectors is to be able to calculate with them. And to do that, let's go back to 2 dimensions. Here's a vector C, and I can break it up into 2 parts. A part in the x direction and a part in the y direction by using the triangle rule backwards. Now, this vector A, I can think of as being a scaling of a unit vector, a vector of unit length in the x direction, which is denoted by I, and then A is just A times this vector I, and the vector B, again, can be thought of as a scaling in the y direction by taking B times J, a vector of unit length in the y direction. That is, my vector C can be written as A lots of I plus B lots of J. And you can do this with any vector. Let's now have a look at another one. I'll take this vector D, which is 4 lots of I and 2 lots of J, like that, and then add to it the vector E, which is 3 lots of I and 8 lots of J. That's 3, 8. If I add those together, then I've got 1, 2, 3, 4, 5, 6, 7 I plus 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 J. That's this vector. And by putting that in there, you can see that all I've done here is to add the i's and add the j's. So to add vectors, all we need to do is to add together the x components and the y components.
So, components of a vector. That's the idea I need here. Let's see how it works in 3 dimensions. Well, I've got a vector in 3-dimensional space here. Also, I've got a set of 3 axes. You see, x-axis along here, y-axis, and up here is the z-axis. 3 axes for 3 dimensions. Now let me put on the components of that vector. Here's the x component along the x-axis. And now let me put in the y component. Here it is. So there we have both the x and y components. But we're not finished yet because there's the z component to put in yet. Well, here it is. So there are the 3 components of my vector. And we could write this down numerically like this. Vector R is the sum of its 3 components. Here's the x component of magnitude x, the number x, and I gives its direction along the x-axis. Here's the y component, and here's the z component of length z units, and in the direction k, which we're using as the unit vector along the z-axis. And of course, to add any 2 such vectors, we simply add the corresponding components. So how does that help us with our problem here? See, we have our 3 forces here acting on the mast. The magnitudes of the forces we can read off on the spring balances down here. For example, this one is 14 units. That one is 14 units as well. And this one at the front here is 8 units. Well, I've got geometric vectors here cut to length, and I can put them in position so that you can see these forces acting on the mast. That one of 14 units length, and this one over here, right at the back of the mast, is also 14 units of length. And then the one at the front, well, that one was 8 units. And these 3 forces here can be added by adding their corresponding components. But of course, before I can talk about components, I need coordinate axes. So let's put in some axes. Let's have the x and y axes horizontal on the deck of the boat. Then the z-axis can be vertical. You can think of the mast as being the z-axis. Now, if we're just interested in the vertical downward component of the forces, after all, that's the force that's acting downward on the hull, then we need to concentrate only on the z components of these three forces. Let me put them in. First, this one, acting down the z-axis like that. Its length, you can get its length easily enough. You know that that's 8 units of length, and it's just 8 times the cosine of the angle between these two. That's just trigonometry, and that gives the length of this z component. And of course, we can do the same for the other components, and I'll place them like this, head to tail, so that you can see how they add. And you can see that they give quite a substantial force acting downwards on the hull. So perhaps you can begin to see the designer's problem there. Also, I hope you can begin to see just how useful this idea of vector components can be.
In this module, we look at the sort of mechanics you need if you're a shot putter.
Tremendous muscular force has to be applied to the shot. First through the legs and trunk, and then through a mighty explosive straightening of the arm. The distance achieved is determined by the speed of the release, the height of release, and the angle of release.
That was an excerpt from a training film for shot putters. You're probably asking yourself, why should we, in an applied maths course, be interested in shot putting? The reason is this: the motion of a shot can be very easily understood just by using Newton's laws. And because the motion is in more than one dimension, then we've got to use Newton's laws in vector form. And that's an important skill that we want you to learn, and you can actually apply it in all sorts of problems in mechanics. Now, what we want you to follow very carefully in this program is the process by which we first of all construct a mathematical model, and then by using previously learned skills like calculus and vectors, make predictions. Now, coaches and athletes are interested in all aspects of shot putting, from the initial wind-up right to the moment that the shot finally hits the ground. Now, in this program, we're going to concentrate on what happens to the shot after it leaves the athlete's hand. Well, in fact, we want to see just how far the three factors of height, speed, and angle contribute to the range of the shot. Now, in order to check just how good our mathematical model is, I've actually got two experts here, Mike Winch and Anthony Zaidman, and they're going to put some shots for us. So, Mike, why don't you put a shot for us, and let's see how the path of the shot actually looks. Well, if you kept your eyes peeled, and it's very difficult to do, it only lasts 2 seconds, you could probably see what the path of the shot is. But in fact, in order to analyze it better, we need a controlled experiment.
This is our controlled experiment. And I'll use this apparatus throughout the program to explore the sort of physics that's important in shot putting. And the beauty of this apparatus is that everything's under my control. Here's my well-controlled shot putter. And this puck is my version of the shot. Now, for this puck, I can control very closely the conditions of the launch. The launcher itself controls the initial speed of the puck, and the initial angle of release, well, I can set that up on this dial. So I've got total control of the initial velocity of the puck, both in magnitude and direction. I can even control the forces that act on the puck after it's left the launcher. You see, there's hardly any friction here, so if the table were flat, there'd be no force acting on the puck. But I've arranged for there to be a small slope down the table. So there's a small force down the table, like that. And you can see that from above. The after images get further apart. And that indicates an acceleration. Now, those after images occur at equal spacings of time. And from their spacing, we can find out the magnitude of the acceleration. In this case, it's 0.06 meters per second squared. Compare that with the acceleration of a shot. And that's the only difference. A puck on this table moves in an exactly similar way to a shot, but everything's slowed down here so we can study the motion at our leisure. Well, now I've introduced you to our apparatus, let's start our analysis. Alan wanted to have a closer look at the path. In fact, this path is a parabola. That's a curve in which y is a quadratic function of x. And in this case, this particular parabola fits the points quite well. The parabola y is 1.6x minus x squared.
In fact, the path is always a parabola. And we can show that quite easily just by using Newton's laws.
And when we apply Newton's laws, this is what we get: a horizontal and a vertical component. And when we solve them, we get this. These equations express x and y in terms of time. But what you want is y in terms of x. You can get that by eliminating t between the equations. It turns out that you get this. That's the equation of a parabola. In fact, it's always a parabola.
Well, everything that goes up must come down. In a parabolic path, of course. Now, all those parabolas were caused by the downwards force of gravity. And here on the table, I can also get different parabolas, this time caused by the force that acts down the slope of the table. Where there's a force, there must be an acceleration. But what does acceleration mean for motion in a curve? And how is it related to force? Well, really, Alan's already given us the answer to those questions, but they're so important that I'd like to take another look at them, this time from a physical point of view. And to do that, I'll need to look at the x and y components separately. In order to see the y component, I'll need to look from down here. So if we can get a camera to come in down to this level, I'll show you what I mean. So this camera will show you just the y part of the motion. .06 meters per second squared in the minus y direction. And that's exactly the same as for the straight line motion you saw before. They're both caused by the force component down the slope of the table. Now let's look at the x component of the acceleration. What would you expect to see this time if we get the camera to move round to give you a low angle view from down here? Remember, Allen's differential equation told us that x double dot was equal to 0. This time, there's no acceleration in the x direction. The images are equally spaced. For each of these paths, the motion in the x direction has 0 acceleration. And the motion in the y direction has a constant acceleration of minus 0.06 meters per second squared. Same accelerations, but different paths. So to understand acceleration in more than one dimension, we need to consider each of the components separately and relate them to the separate force components. So, what is it that influences the path a puck or shot will take? Well, in fact, you had the answer at the very beginning of the program. It lies in the initial conditions, the way in which the particle's launched.
Let's now go back to the shot putter and the problem of the maximum possible range.
So let's recap what we know so far in our build-up of the model. Well, first of all, we know that the path of the shot is a parabola, and the precise shape of the parabola depends on the initial velocity, on the speed of launch, and on the initial angle of launch. Well, let's suppose the shot putter uses his maximum effort, and that this leads to the same initial speed no matter what angle he puts at. So the initial speed's fixed. And that just leaves us with one factor to consider, the angle. Now, this is the problem we'll be considering for the rest of the program. What's the optimum angle the shot putter must pick in order to get his maximum range? Well, before we can answer that question, we really need to investigate a bit further the connection between range and angle. And to do that, I'm going to come back to this apparatus. Now, the problem I'm going to consider is to try to hit this target. It's actually 1 meter away from the launcher. The launcher's at the origin, and I'm going to try to hit it. So I've got to find the right angle at which to launch. Let's try this one. It's about 40 degrees. It's gone a bit far. .35 degrees a lot nearer. Come right down here. 15 degrees. There. So, to hit a target 1 meter away along the x-axis, I have to launch at 15 degrees.
Well, experiments are all very well up to a point, but if you want a general connection between range and angle, then you've got to go back to theory. Theory is represented by our two equations, x double dot equals 0, and y double dot is equal to the acceleration. In John's case, that's 0.06 meters per second squared, and I've represented that by the symbol a, so it's minus a. Well, you're probably quite quick at solving these equations now, and you get x equals at, and y is equal to this quadratic expression in t. And there's no additive constant in this case, because the particle starts off at the origin. Now, we're interested in the range, that is the value of x for which y is 0. So let me just put that in. X equals r, and r equals a times time, and I'll assume that that occurs at time capital T. Now, what happens? Y is 0 at t, so I can substitute for this equation, and I get a quadratic in t. Now, there are two values of t which satisfy it. One is t equals 0. Well, I can discard that. That just corresponds to the starting time. But the interesting solution I get from the other one, which is t is equal to 2c divided by a, and I can substitute back, and I get r is equal to 2a, t is capital C, divided by a. So let me rewrite this. R is equal to 2ac divided by a. Well, that looks very simple, but in fact, what do these constants a and c mean? Well, let's go back to our equations to see that. If I differentiate x with respect to time, I see x dot equals a. So a is simply the initial x component of velocity, the horizontal component of velocity. And what is that? If the speed is v and the angle is theta, then the initial horizontal component is just v cos theta. So I can substitute. And what about capital C? Well, go back to the y equation, differentiate, and I get something times time plus c. Now, when time is 0, that's initially, I see that y dot is equal to c. So, in fact, c is just the initial vertical component of velocity, so that's just v sine theta. And I can simplify this expression a little. V times v is v squared, and 2 cos theta sine theta. Well, if you remember your trigonometric identities, that's just the same as sine 2 theta, and then I divide by a. Now remember, we're looking for theta, so I can bring sine 2 theta to the other side, and I get sine 2 theta is equal to AR divided by v squared. Well, that's a very simple expression. I wonder if that checks with what John got. Well, remember, John, he had 0.06 for his acceleration, and r is 1, and his v is a third. So I'm dividing by a ninth, I'm multiplying by 9, I get sine 2 theta is about 0.54. It's about a half. Well, I have a graph which will help me calculate what theta is. When sine 2 theta is a half, that's about here, I find that theta is 15 degrees. And that checks with what John got. So the theory is good. It actually confirms the experiment. But theory is better than that. Theory can actually make predictions. And I can see from this graph that if I take the same value of sine 2 theta, that is the same range, then there's actually another value of theta, which should give me that same range. It's about 75 degrees. So that's a prediction from my theory. I predict that at 75 degrees, John ought to get the same range again.
So, does that mean that shot putters have a choice to attain their maximum range? Well, certainly there are two launch angles for this range. The lower curve has a larger velocity component in the x direction, but it doesn't stay in the air for so long. The upper curve, on the other hand, has a smaller velocity component in the x direction, but it makes up for this by staying in the air longer. Eventually, it reaches the same range. Different ranges will be achieved by different pairs of launch angles. But there's no choice of launch angle for the maximum range. It's achieved when the launch angle is 45 degrees.
And we can actually get that from theory, because if you look at our expression for the range r, it's v squared over a times sine 2 theta. Now v, the speed, and a, the acceleration, are constant. So the range will be a maximum when sine 2 theta has its maximum value. Well, let's go back to our graph and see when sine 2 theta has its maximum value. It occurs here at 1, and that's for angle 45 degrees. So in fact, our theory does predict that the maximum range occurs when the launch angle is precisely 45 degrees.
So, that's my maximum range. There should be no way that I could actually get further than that. But wait a minute, supposing I cheat a bit. Supposing I actually move this up here. Okay, a greater range. And it's easy to understand why that happened, because I'd moved the launcher further up the slope.
And that corresponds to shot putters throwing from a height h. So what we want is tall shot putters. We already know maximum range is attained from a launch angle of 45 degrees. That's if we launch from 0 height. And by increasing the height, still launching at 45 degrees, we increase the range. Now, I suppose that if I launch at an angle of less than 45 degrees, well, the range will be less than maximum. Or is it? For shot putters of non-zero height, the maximum range is achieved with an angle of less than 45 degrees. Let me explain why that happens. Both shots start off with the same speed, but the lower shot has a greater horizontal component of velocity and a smaller vertical component of velocity. So that by the time they get back to their starting height h, you see the lower shot is lagging behind. But at this point, it's got a greater forward velocity and it's dropping more slowly, so in fact it can actually overtake the steeper shot. Now, if we were to launch at a shallower angle, say 0 degrees, too shallow, then it would just drop down. It would never catch up. So there must be an optimum angle between 0 degrees and 45 degrees. And we can find what that optimum angle is by separating out the x and y components as before. But that's your problem after the program.
The fabulous perfect spring, a device which produces motion which is both perpetual and simple harmonic. This module is about simple harmonic motion. So, how do we model this system? That's done with this equation. Mass times acceleration equals force. What's this k?
Well, k here is a positive constant, which is just the stiffness of the spring. L0 is just the natural length of the spring, and x is just the position of the mass at the end of the spring. Now, this differential equation is good whether we have extension or compression. It's good throughout all stages of the oscillation. Well, what about the solutions to this differential equation? Well, that depends very much on the initial conditions. You can see what the solution looks like if the spring is stretched and the particle released from rest. This shows how the position of the particle varies with time. It's simple harmonic. This is the solution for the initial conditions we used. The general solution to this differential equation is of this form. X is just a cosine function of time. Now, what about these numbers which occur in the solution? Well, omega and L0 are just numbers which are intrinsic to the system. For example, L0 is just the natural length of the spring, and omega, well, omega is the angular frequency measured in radians per second, and omega is given by this expression, the square root of k over m, where k is just the positive number, which is the stiffness of the spring, and m is just the mass at the end of it. And that determines what the period is. You see, because this is a cosine function, it repeats itself every 2 pi, and so every time t changes by 2 pi over omega, we get back to where we started. So the period is given by 2 pi over omega, and I can represent this as the period. Now that period is the same for large oscillations and for small oscillations. It doesn't depend how we set the system in motion, and that's a very distinctive feature of simple harmonic motion. Well, what about the other numbers which occur in the solution? Well, they do depend on how we start the system in motion. A is the amplitude. It tells us how far we get away from the natural length from the static solution, and that really, in this case, depends on where we start off the mass in motion. Phi, well, phi is called the phase. It's measured in radians, and that really tells us how the motion started when t equals 0. So again, the phase depends on the initial conditions. In this case, phi is 0. And here phi is pi by 2. Here are two solutions that differ only in phase. Remember, for the left-hand system, phi is 0, and for the right-hand one, phi is pi by 2. Each system oscillates in the same way, but at a different time. So the difference in phase expresses how far out of step they are. So now we know all the features of simple harmonic motion as predicted for the perfect spring.
Unfortunately, I haven't been able to get my hands on one of Alan's perfect springs. That's not too surprising, because they're really only a figment of his mathematical imagination. In the real world here, no spring can keep an object oscillating forever. But we can understand quite a lot about real spring mass systems by using Alan's model. I shall model this object by a particle of mass m, and this real spring by a perfect spring of stiffness k. Now, thanks to the air track, there's no other force that I have to bother about.
And so the prediction is simple harmonic motion with a period determined by m and k. The period is independent of the amplitude. And what's more, the period is just the same for vertical oscillations. The constant force of gravity has no effect on the angular frequency. The only difference is that the spring is extended in the static position. To change the period, I must change the mass or the spring. And an increased mass gives an increased period. The angular frequency goes down. If the spring stiffness is doubled, we get the opposite effect. And combining the effect of increased mass and increased stiffness gives a system with the same period as a single mass and spring. And that's still true even if I arrange the springs differently. And finally, an interesting system that we'll be studying later in the unit. Two particles, each of double mass, connected by a single spring. Again, the same period as our simple system with the single mass and spring and one end fixed. Well, all those systems can be analysed in the same way, by modelling the springs as perfect springs, by applying Newton's second law and then solving the resulting differential equations.
But that's not the only way of analyzing oscillating systems. Some problems are better tackled using energy conservation rather than Newton's second law. Now, for our perfect spring mass system, the total energy E consists of two parts. There's the kinetic energy, which depends on the speed of the particle, and this potential energy function, which depends on where the particle is. The more the spring is extended or compressed, then the greater is this potential energy. Well, what is the precise form of this potential energy function? Well, it depends on the force F that occurs in Newton's second law. For the total energy to be constant, the potential energy must be just minus the integral of the force. Well, we know what the force is. It's just the right-hand side of our expression for Newton's law. In our case, minus k into x minus L0. So now when we integrate that expression, then we're going to get the following result. Now you see, that integral involves an arbitrary constant of integration, which we're free to choose. And surely a natural choice is to say that when the spring is at its natural length, then the potential energy it has is 0. And that involves in choosing that constant equal to 0. So this is the expression for the potential energy of a perfect spring. So this is our energy conservation equation for the perfect spring. Now, it involves the speed and the position, and it helps us to relate these things without having to go through a calculation involving the equation of motion and time. And really, that's the main virtue of the energy conservation equation. The total energy of the spring mass system is constant, but the two parts of it, the kinetic energy and the potential energy, are continuously changing. So let's have a look at that. In the static position, the potential energy is 0. When the spring is stretched, it acquires potential energy. This energy becomes the total energy of the system, which we've called E. Once released, the potential energy of the spring changes continuously throughout a cycle. The maximum value of potential energy is E. It reaches a minimum when the spring has its natural length. At this instant, the kinetic energy has its maximum value, which will be the number E, since E is the total energy of the system. In full compression, the particle is instantaneously at rest, its kinetic energy is 0, its potential energy E. Again, at the natural length, the reverse holds. at any instant in the cycle, the sum of the two energies must be equal to E.
The fabulous perfect spring mass system at the bottom of the screen has potential and kinetic energy. Potential energy, shown in yellow, and kinetic energy, shown in red, sum to a constant. Does knowing that help us to understand simple harmonic motion in a straight line?
For motion along a straight line, with forces that depend only on position, you can choose between energy conservation and the second law. And after a little practice, you'll soon learn to decide which problems are best suited to which method. But here's an interesting system where the motion isn't along a straight line. And it's really quite easy to understand those oscillations in terms of energy conservation, whilst it's not immediately clear how to apply Newton's second law. So let's look at this system in the same way that Alan looked at the perfect spring, by analysing the interchange of kinetic and potential energy. Well, instead of a spring as our source of potential energy, we'll be considering gravitational potential energy. On the way down, the kinetic energy will increase as the potential energy decreases. Now, at the bottom, the potential energy is a minimum, and so that's where the kinetic energy will have its maximum value. And on the way up, of course, the kinetic energy will decrease as the potential energy increases. Now, the car almost gets to its original height. Not quite, because of friction and air resistance, which also plague real spring mass systems, as opposed to Alan's perfect ones. Now, the same interplay between gravitational, potential energy, and kinetic energy will occur on any shape of track. The details of the motion will clearly depend upon the shape of the track. And I'm certainly not claiming that that is simple harmonic motion. But near to any minimum of potential energy, like this one, the oscillations don't look very different from what we saw with the spring. So, how can we use energy conservation to predict what will happen near to a minimum of potential energy? And what sort of motion do we get?
Well, let's generalize what we did for the perfect spring. Suppose I have a particle whose position is described by just one variable. Now, that variable could be the length of the spring, for example, or perhaps the distance along one of David's curved tracks. Well, in that case, the energy conservation equation is just kinetic energy, a half m the speed squared as usual, plus u of q, which is the potential energy function. Now, David tells us that we're interested in what happens near a minimum of u of q. Now, what do we mean by a minimum? Well, by definition, if u has a minimum at q0, then the first derivative is equal to 0. Well, in fact, that could be a minimum or a maximum, but it really is a minimum if the second derivative at q0 is positive. Now, let's use these conditions to find a nice approximation for this potential energy function near the point q0. Well, I'm going to do this by means of a Taylor's expansion. So, I have a first term, a constant term, which is u of q0, and then I have my linear term, which involves the first derivative. Then I have a second derivative, and really, I'm going to stop here, so in fact, this is only approximately equal. I'm neglecting the higher terms. Well, it still looks a bit complicated, so let me simplify. First of all, the constant term. Well, I can choose the potential to be 0 at the minimum point Q0. Remember, that's what we did for the perfect spring, so that gets rid of the constant. Now, the first derivative, well, at a minimum, that's 0 anyway, so this term goes out. And in fact, I'm simply left with this rather simple expression for approximation near Q0 in terms of this second derivative only. Well, where have we seen something like that before? Well, if you compare the energy conservation equation for the perfect spring, you'll see that it's precisely the same form as our approximation, except I've written Q in place of X. Well, that's very interesting because it tells us that in the general case, we've got approximately simple harmonic motion near the minimum Q0. In fact, if the potential energy function U of Q were perfectly quadratic, then this would be exactly equal, and we would have exactly simple harmonic motion. But as I say, in the general case, when it's not quadratic, it's just an approximation. Well, that's interesting, but we can even make a far more interesting prediction, because we can find out from this expression what the period is. Remember, the period for the simple harmonic motion is just defined as being 2 pi over omega, where omega is the angular frequency, and the angular frequency is given by the expression root k over m, where m is the mass. And what is k? Well, if we compare expressions again, k is just the coefficient of this term, so in our case, it's just got to be the coefficient of this, which is the second derivative. So in fact, we have this equality, and that gives us a very general expression for the period of this simple harmonic motion near a minimum of the potential energy function.
So I can use Allen's general result to predict the motion near the bottom of a curve like this. Now, my variable q, which defines the position of the particle, is the distance measured along the curve. And the kinetic energy is a half m q dot squared.
U of Q, the potential energy, is the mass times g times a function h of Q. That depends on the shape of the curve. H of Q tells you how high any point at a distance q along the curve is.
So now the period is given in terms of things which I can calculate. The period, 2 pi over omega, is given in terms of the mass and k, and you remember Allen's result, that k is just the second derivative of the potential energy function at the minimum. Of course, I have to remember that the prediction is only approximate simple harmonic motion near to the minimum. If I want simple harmonic motion for large amplitudes as well as small, then the potential energy function has to be an exactly quadratic function of q. And there's only one curve for which that's true.